Okay. In the last class, we talked about the column and we just gave you the fundamental idea that what is column, how it is look like, what type of load it is carried, right? That's what we just described. But if I told you to design a column, you cannot design without knowing the formula, how we will figure out the stress in the column. So you need to know a formula. So that's what we are doing over here. And normally we have three formula in column. Number one is called Euler equation, that is used for long column. Other one is Johnson equation, that is used for short and intermediate column. And we have third formula, that is for column with eccentric load. That means you apply load, but load is not going through the center or CG of the cross section. But Euler equation and the Johnson equation we will use. In that case, load will pass through the CG or centroidal axis of the column. So we will start to derive the Euler equation of column, and sometimes it is called equation of a long column. Okay, so at first we are considering a long or slender column of length L, long or slender column of length L, cross-sectional area A. We already, I think this must we already discussed it, but I am repeating it. And it's subject to axial compressive load P. The bar is remain in deflected shape between the pin. So if we are able to figure out the value of the P, that will be critical load, because the maximum minimum value of P that it can hold in a deflected shape, and it can carry that load without failure. That means if P we found 500 pounds or 500 Newton, but you increase it will be like 510 or 505, then column will fail. Okay. So what are the assumption? That cross section of the bar is constant throughout the length. That means no change of cross section. Material of the bar is homogeneous and isotropic. A material of a Hooke's law. Compressive load P is acting through the centroid of the cross section, and also the load passing through central of the cross section. That are the assumption. Now we will derive. So we already told you before that column and beam, it is deflect, right? Either upward. In column, it might be deflect upward or downward. Any direction it can deflect. Right now, just we showing that it under load, it deflected toward upward, but it might deflect it like that. But in case of beam, if we apply load from the vertical direction from the top, then it will deflect like that. Okay. So this deflected shape is a portion of a circle that we already described it. And why it get deflected? Because at every point, bending moment work in the column. And this deflected shape has a certain radius, right? That is called curvature of radius. So this curvature we think is rho. And elasticity of the material is E, and section property, that means moment of inertia, is I. Okay. So relationship between bending moment and the elasticity is M equal to EI by rho. And this radius of this curvature, it is described by this equation. This coming from the mathematics. Now, this equation, if you expand, then you will get dy by dx to the power 3, 1 plus 3. So if you ignore the higher order term, then we will get 1 by rho equal to this one. Now, over here we have 1 by rho. So we will, value of 1 by rho will substitute in equation 1. Now, let me see, we might have free body in the also in the next slide. Yes. So you see in this slide, what we did, we take a point at point A. And what is the location of point A? You see, this is the longitudinal axis of the column along x direction, and along vertical direction is y. So point A, it has coordinate, right? X and y. So we are thinking in vertical direction, the distance of point A is y. And in horizontal direction, distance of this point is x. And this point at point A will cut the column. And we'll try to make a free body, and we'll see what type of force is working. Right now, you cannot see the force at point A, right? So after we make the free body, you be able to see the force, and that force will be internal force. So right over here, cut it. So at point left side, P working toward right, right? So at the point A in the upper side, the P should work toward left. So this P is working along this left side. Okay. So could you hold on just 1 minute? I have imagined. Sorry about that. We need to proceed. Okay. So right over here, you able to hear me? Hello?
Yes, sir. Yes, sir.
Okay. So look in the right side free body. What we did, from the left side, we have force P. From the right side, then it has to be on P to make it balance, right? Now, what you see? If we put only the P, so this is my column, say this is point A, this is the left side. Now, this side have force P. So obviously this side will have force P in opposite direction. Now what happening? This is rotating because there is a distance between these two forces, right? Like this one, this height, right? This is some distance. And so this will try to rotate in anti-clockwise direction, right? Along this direction, it will try to rotate. So if we don't know that how much moment is working over here, but if I say moment working M right there, we are thinking a moment should work opposite direction, right? If you figure out the reaction, but we are taking along this direction. We are saying this is the M. This is the mx. Okay. Now, how will you figure out if you take moment this point, then what will you get? So there will be no moment for this force, right? You will have moment this force, that means P, and for this distance. So if you think anti-clockwise is positive, then you will get mx plus P into y, right? This equal to 0. That you will get equation. That means value of moment you will get P into y. And this value of moment is different value of x, because is x increase or decrease, y also increase or decrease. That means m varies with value of x. Now, these two force P try to rotate in anti-clockwise direction. But when we look over here, and even reaction, I am saying rotating also anti-clockwise. Actually, that's not right, right? Because this force working this direction, right over here working this direction, right? So this object try to rotate anti-clockwise. Again, I am putting reaction anti-clockwise. This is not right. It should be clockwise direction to protect the rotation. But for simplification, I put the same direction. So what will be happening? My value will be negative. That's all. After calculation, if you got minus 10 Newton meter, then it will be positive. Okay. So go through next slide. This is our equation. That 1 by rho equal to this mass and m equal to e by rho. So this 1 by rho value we'll put over here. So we will get 1 by rho equal to d square y by dx square. And 1 by rho, right over here, 1 by rho equal to m by ei. M by ei, 1 by rho. So now we figure out the value of mx. Instead of m, I am putting mx. Why mx? We are thinking that m is a function of x. Now, how we'll figure out this value of mx, we need to figure out. So what we did, I take moment at point A and thinking that clockwise is positive. So p into y, right over here, no moment for this p. In the for this p, there will be no moment because force into distance is 0. For this p into y, and is rotate clockwise. I'm sorry, anti-clockwise. So this negative. P into y is negative right over here. And mx also same direction, so both negative. So I'm saying minus mx minus py equal to 0. Now we are getting mx equal to py. And this value of mx equal to py we will put right over here. Then what we'll get? We will get a differential equation. And we will solve that differential equation by using mathematics. So you see, we are getting this one. This square y by dx square equal to minus py divided by ei. So what you see that if you apply a load in a column, then amount of load will be constant, right? That p value is constant, ei also constant. So p by ei, this value will be also constant. So we are thinking that this value equal to k square, p by ei. So k equal to root over ei, or you can say we are thinking k equal to root over p by ei. Why we are putting this one? Just for our convenience. So d square y by dx square plus k square y. Okay. Now we try to solve this equation by mathematics. So since this course is not the course of mathematics, so we just use the mathematics. And this is second order differential equation. So if you look the type of differential equation, that how we can solve it. This one like is coming like d square y by dx square plus m square y equal to 0. And you see in the, you open your mathematics book, and you can see what is the solution of this type of equation. So solution become yx equal to c means a constant. You can say c1, c2 plus sine kx plus c2, then now we put d constant plus k into kx. So this is our equation of y. So what is actually y value? And right now what you see that y is a function of c, function of constant d, and function of k. And k value is right over, k is a constant, right? So y will not depend, it will depend on k, but k is not varying, only x varying. Now, how we can solve this differential equation? We are able to solve it, and when for minimum value of y, you will get the p critical. So we need to figure out what will be the minimum value of y for the load. And also we need to figure out the value of these two constants, C and the D. So value of C and D could be found from the two boundary condition. Number one, x1 equal to 0, y equal to 0. You see, if x 0, then there is no deflection at this point. That means y is 0. Then if you put x equal to L, then you are right over here. Then what will you get? You are getting y 0. So we put x equal to L, yl equal to 0, x equal to 0, and y0 equal to 0. Okay. Then we solve that differential equation. So you see, we got two boundary conditions. Number one, x equal to 0, y equal to 0, x equal to L, yl equal to 0. These two boundary conditions we will use to solve in equation 5. So you see, applying boundary condition 1 in equation 5. So you put x equal to 0, the sign 0 equal to 0. So this value, this value will be 0, right? And y value will be 0. So ultimately, what are you getting? Cos 0 equal to 1. So you get d equal to 0, right over here. So we are getting constant d equal to 0. So what is our equation coming? Yx equal to c into sin x. That is our equation, right? Then we put the second boundary condition, this one, x equal to L. So x equal to L, we put YL equal to sin KL. D, we got already 0. So this is this term coming 0. So finally, ultimately, you are getting, you see, the sin KL equal to 0. Because what is the value of YL? At length L, deflection 0, y0. So that's why we put 0 over here. So that means sin C sin K equal to 0. Now, the value of C, it can be 0. Already we found D equal to 0. So if you found C 0, then what will happen? This equation will be invalid. That means there is no deflection of the column under load. So value of C cannot be 0. So which value will be 0 then? Obviously, the sin KL, this value will be 0. And we know the value of KL equal to this much. So we put sin KL equal to 0. Now, when sin value can be 0, like sin, if we put sin 0, then what will happen? If you say the sin 0 degree is 0, right? Sin 0. Sin 180, also 0. Then sin 360, also 0. If you increase at the rate of 180. But if you put n equal to 0, then what will happen? Sin 0 equal to 0. You put n equal to 0, then sin 0 equal to 0. You cannot put n equal to 0 because already d value is 0 we found. Again, we are saying sin kx equal to 0, then yx will be 0. That means what they are saying that the value of sin kl equal to sin n pi. But value of n will vary from 1 to certain number. So that's how we put sin equal to n pi. Then okay, sin kl equal to 0, this equal to n pi. And both sides, you take out the sign. So you got root over ei into L equal to n pi. You got this n pi. Okay. Now you make it square. Whole side, take out the square root and try to figure out the value of p. This is value of p. What is our target? We like to figure out the for minimum value of p. So you see, for minimum value of p value will vary from 1, 2, 3, 4. So if p n equal to 1, then p will be smallest for minimum. So the value of p will be minimum or smallest or critical for n equal to 1. And for minimum value of L, this will be L, you know, which is called first mode of buckling. The load is given by, no, on second. This is not, this is I. For minimum, you see, right over here, we got the I, right? EI by L square. So P will be minimum when N value minimum and I value minimum. And before we show you in the last class that we have two I along two axes, Y axis and X axis, and from these two value, one I will be minimum. So critical load, we are getting pi square E I minimum by L square. And we know that radius of gyration equal to I minimum by A root over. So what we can do, if we want, we can replace this I with this value. That we did in the. So you see in the equation, when you replace I by I minimum and replace the N by minimum value, then it is no more P. It will become P critical, okay, or minimum value of P. Now, we can simplify this equation just by rearranging. Right over here, we have this equation, right? I minimum. Then I minimum equal to rho square A. So this I minimum, we put over here, inside over here. So you replace I minimum by rho square A. So you got this equation. Okay. So pi square EA, then you are getting L by rho square. Now, this A you are beginning the left side. So you are getting P critical by A equal to pi square E L by rho square. So you are getting sigma critical equal to pi square E L by rho square. Where the L by rho is called slenderness ratio that we already discussed it in the last class. So the above equation is known as Euler equation for long column, this equation. And sigma critical is known as critical stress of column. Above formula is derived for pin-to-pin support. Now you see that I already told you that support of the column might be pin-to-pin, might be both and fixed. Now you see what we get. We derive this equation for pin-to-pin support, right? Then how you will use this equation for like a pole that has fixed at the underground, one end fixed, and other end carrying load, compressive load. How we can apply? Because we derived only pin-to-pin support, but this is not pin-to-pin support. So that's why what we need to do, we need some adjustment in the equation. What is the adjustment? Right over here, we put some constant. That constant is called N condition. Where we put N condition C. So sigma critical equal to pi square EC L by rho whole square. What is the C? C is the N condition. Now, tell me if we use this equation for pin-to-pin support, then what will be value of C? Anyone? Value of C? Tanvir Hassan. You can tell me what will be value of C for pin-to-pin support?
No, sir. I think
No.
I have
You
lack
guess.
of knowledge here.
One.
Should be 1. Thank you. 1 because it's matched with the whatever we derive. So that means when you work for a pin-to-pin support column, then you will put value of C equal to 1. Okay. But other end conditions, say you have one end fixed, other end free. You see, this will be weak column. So this will take less load. This column, you need to figure out what will be its length if you want to exchange with pin-to-pin column. That means if this column carry load 100 pound or 100 Newton, a pin to column, figure out the length of the same column, that means with pin to pin support, how much the length. So you might get this length might be, this is called equivalent length. Equivalent length of the pin to pin support. You might get equal to, for example, if this one 20, you might get this one equal to 40. That means a 40-meter long column, pin to pin support, and a 20-meter long column, one end fixed, one end pin, will carry the same load. Okay. So from this concept, we have one more term in the column chapter that is called equivalent length of the column. And this equation, an equivalent length of the column, normally we say that LE, equivalent length of the column, LE equal to L by root over C. This is the equivalent length of the column. And this equivalent length of the column, we can, that means what I like to say, the Euler equation we can express in terms of equivalent length of column. So you see, this is L by K square. What I put in the previous equation, let's see. I think we put rho. 1 second. Yeah, we put rho over there, L by rho. But rho and K is the same thing. By mistake, I put the K. Some book expressed by rho, some book expressed by K. So we are getting pi square is C, L by K square, right over here. So L by K square. Now this C, I can take it in the bottom. So then it will be 1 by C. Now I take it out 1 by K square, and this L square we put in the bracket, this L square. So in the bracket, what are you getting? L by root over C, right? So L by root over C, we can say this is LE. That means this term, L by root over C equal to LE, L by root over C. So you get then LE square. So finally, you are getting LE square divided by 1 by K square. So pi square is C, LE by K square. So this is also a different form of Euler equation, a simple form. So what you see in the Euler equation? You see your critical load. If you got the critical stress, you can figure out the load because load equal to sigma critical into area. So another thing you see, we put EC. What is EC? Compressive modulus of elasticity. And in your solid mechanics, Shana Satish use the stress strain graph, right? That graph normally we derive for tensile load, and we figure out the slope of the graph before yield point, and we figure out the, right, we have this one, then you have this one. So slope of this graph is value of E. But this one, actually in the book you see they say only E, but this is called tensile modulus of elasticity. But what will happen when you compress something? In column, we are compressing something, right? So instead of ET, we are using EC. That means compressive yield strength. Normally in undergrad level, all the book you will see they use only E, not EC or not ET. But in real world, you see they are giving a material for both value. So you working in the aircraft industry, working in a missile defense industry, or a shipbuilding industry, then you see value of E is not the same. Compressive and tensile is little bit different. But there is a thumb rule. that for ductile material, if we have a ductile material, then for ductile material, compressive modulus of elasticity and tensile modulus of elasticity is almost same. That means EC equal to ET and E. But if metal is brittle, then it's different, because brittle has more compressive strength. So what happened right over here, that we normally the compressive elasticity of a ductile material will be same as tensile elasticity. That means for ductile material, modulus of compressive elasticity and modulus of tensile elasticity is same. So right over it's a column carry compressive load only, need to use compressive modulus of elasticity EC. Remember, for ductile material, both is same. Okay, just remember this one. Now, what is the equivalent length? Equivalent length equal to this one, that we say equivalent length is this one, right? L by, what is the L? L is the physical length. What is the LE? Same beam for both end pin. For example, I am taking this column in the figure A. Okay, I'm saying this length, I mentioned LA, that means length of figure A is 2.5 meters. So obviously it will carry some load P, right? For pin to pin support. And we can use the Euler equation because it is built for pin by pin. So that's why for this pin to pin support, C equal to 1. But if you look this column in the figure B, this end is fixed. Also this end is fixed. So it will carry more load because this end condition is stronger than the left side one. So I like to convert this one into pin to pin column. So obviously if I made longer, then it will carry less load. But if I make shorter, it will carry more load. So this column, this one, will behave like a pin to pin column, only this much length L by 2, this column. That means this column and a column with pin to pin end and this much length will behave the same. So that's why value of LE is coming half of this column. This column, what is the length? 2.5. Physical length, all of them is 2.5, I consider. Okay. But if you convert this column, then the length will be E equal to half of this one. That means 1.25. What does it mean? That value of C in that case will be 4. L by root over 2. Root over C. C equal to 4. That means L by 2. So length of this column will be half of this column, 1.25. Now, similarly, in the right side, figure C, this is more weak. You see, only this end fixed, other end is nothing, is free. So this length has 2.5 meters, but if it will work like a 5 meter column with pin to pin end. It work like a this pin to pin right over here, pin to pin right over here. So that's why is value of C equal to 1 by 4. 1 by 4 mean actually is coming 2L. So that's why for C, for a column C, equivalent length is coming 5 meters. Okay. Similarly, right over here, you see this column has a fixed end, this one has a pin end. So for this column, little bit stronger than this one. Okay. So if you like to convert this column in a pin to pin column, then you have to take only 0.770L. So you multiply, that means value of C will be only 2. So LE will be L by root over 2. And that's why it's coming 1.77. So what is the L? Physical length of the column. What is the LE? Length of equivalent length of pin to pin column of same column. I'm giving you a 5 feet column, both end fixed. So you're making with the house in your building. You're making a house. But instead of pin to pin, if we fixed to fixed, if you use pin to pin, but you want to carry the same load, then what will happen? You need to make column more shorter. Okay, that is the criteria of equivalent length. And why you are doing? Because we apply the Euler equation in all end conditions. That's why we figure out the equivalent length of column. So far, any question? Anyone has any question? Hello?
Sir, on the first, when you made a cut through a column, why there is no shear force?
Why you make a cut? Okay.
Yes, sir.
And you say what is the shear force, right?
Yes.
Very good question. Because column is bent like that, right? And is taking load, this and compressive load. And you see there is no load along this direction. So what I did, I cut it anywhere you can cut. So for example, I'm cutting right over here. I'm not cutting here. This is my external load. Load you apply externally, right? Now, I like to figure out the force right this point. By how? By applying your rule from your statics. Summation of fx, my, and summation of moment will be 0. Because we are working with the static body, not the dynamic. So this is say 10 Newton. So obviously it has to 10 Newton, right? And you see there is no other force. If there is a vertical force over here, then you can put say vertical force working right over here downward, then over here will be upward. So this force is working parallel to the surface, then there will be shear stress and shear force. But since we don't have this force, so we will not have this force, that means we have only normal force. And this force passing through different point, that means we will have a moment. So is clear to your, you got your answer?
Yes, sir.
Okay, but thank you. I always appreciate all of you for asking question. And what is your ID?
Sir, 18.
18. Okay. Ronnie, Ryan,
Rion.
18. Your ID 18, right?
Yes, sir. Rion Shaw.
Okay. Actually, we are giving you the mark for the attendance. Actually, that mark is not attendance. That is called class performance. That whether you are asking any question in the class or not, or if your teacher asks some question, you able to answer it or not. It don't matter. It is wrong or it is right. But you giving the answer, what does it mean? That you have some intention to learn and you have some confusion inside, but you like to remove that confusion. Okay. So actually we should give the number in that same way, but normally a lot of faculty do that. I normally don't do, but sometimes I do. I remember the name of the student and ID that he is responsive in the class and asking some question and also giving answer of this question. So I appreciate you for asking question. Okay. So let's go through the next slide. That what we have. Now you see, okay, I can give you 5-minute break after one class is finished. Is already one class finished?
So,
Hello?
Sir, only 3 minutes left.
3 minutes left. Okay. So right now is 10:28, right?
Yes,
So
sir.
you come back at 10:34, then we will start a new formula. So what happened is, see, we derived the Euler equation, right? And before we derive, we already mentioned this is used for long column because I know it, so I am saying. But what happened if we have a very short column? Then which equation you will use? Other thing, how will know a column is long and short? You cannot only by seeing the length, you cannot tell that this is a long column, this is a short column. Even sometimes a column is physically very short, but it might behave like a long column. So what we'll do, after you come back from the break, we will derive Johnson formula for short and intermediate column. Okay, so I'm giving you 5-minute break. Then you